Greetings, Guyworthy here. I'd like to talk about galaxy evolution and a new technique for uncovering that evolution. So galaxies are the kind of one of the fundamental units of the universe. It's a big parcel of stars and gas. And as we see them around nearby, we wonder where they came from. So the key questions about galaxy evolution are: when did a given galaxy form its stars? How many stars at which epoch did it form? And was the character of it bursty or continuous? And if you use cosmological models, does the predictions from those models actually match what galaxies do? The main clue we have is the spectrum of a galaxy. So here is the spectrum of NGC 205, a nearby dwarf elliptical galaxy. There's a lot of structure in there, in that spectrum, and it would be nice to be able to exploit that, and we do, in kind of crude ways. So we have to improve what we can do. So the idea behind this new technique is to take a look at star clusters, and a star cluster can be considered as a subunit of a galaxy, kind of a simple galaxy all by itself. The pictures of the Pleiades star cluster, and if you take the star census one by one, the luminosities of the stars we can plot on the y-axis, and then a color or a surface temperature we can plot on the x-axis, and we end up with this HR diagram, a luminosity temperature plot. There's a lot of structure there. It's not random at all. That's called the main sequence of stars. And that main sequence is understood as a mass sequence, but massive stars live fast and die young. So as a population, a cluster-like parcel of stars evolves, the first to go are the massive stars, and then it unzips down the main sequence until it reaches really, really long-lived stars, such as the Sun, which lives for 10 billion years. The new technique is that we've noticed that there are some categories of chemically peculiar stars that line up along the main sequence. This isn't every type of CP star, but it's a good smattering of them. And they tend to lie in narrow temperature ranges. So the new technique is to exploit that. If the unzipping happens, it will pass through each of these chemically peculiar star categories on its way. Now, CP stars are the minority, but there is enough of their starlight to be detected in the end. And the peculiarities in their spectrum are pretty strong. So here's an example of a black normal star and then a purple Mercury manganese star. And you can see there are quite a few more absorptions due to the enhanced abundances in these chemically peculiar stars. So the project to date is we have included those CP star spectra into the models for our galaxies, and we have computed the models to compare with real galaxies. We have adequate data to compare with. And then what remains to do is to chart out how best to extract the information we want on ages and to optimize a routine to get a statistical handle on it, and then finally to produce some results for nearby galaxies that are well observed. And so that, in a nutshell, is how we plan to improve our understanding of the fossil record of the star formation of a galaxy.